Alright guys, welcome to the Wednesday directions video. Today we're just taking notes on earthquakes and connecting it kind of to our plate tectonics. So I'm going to go through the notes with you guys right now. Like I said, about 1/5 of the test questions come from today's PowerPoint, so make sure you're paying attention, jotting down everything in red, and we'll just get right into it here. So obviously earthquakes are a factor, or they're more of an outcome when we're talking about plate tectonics, and that's kind of what we're looking at here. So our learning goals today, I'm just going to read them for you guys, the essential questions that we're trying to accomplish. You guys can't really see them, but it is. Number 1, relate earthquakes to plate tectonics. Number 2, define the focus and the epicenter of an earthquake. Number 3 is describe the wave types. And number 4 is what tools measure magnitude. So if you want to pause and rewind or write those down, because again, those will be the board questions for tomorrow. So let's dive into it. The objectives are the same things that I was kind of talking about. Here's kind of our essential questions we're trying to answer. But let's just get right into it. And again, we're only jotting down the stuff in red today. So why do earthquakes occur? Well, we know they occur at fractures and faults, as you can see here. I wonder if I can make this bigger for us here to make it easier for us to see. All right, and we just want to know energy released and propagates in all directions as seismic waves causing earthquakes. I think we kind of know that. We talked a little bit about the transform plate line, where they get stuck, and when they release that energy from the release, shocks seismic waves throughout the earth, and then we get an earthquake. So let's kind of go over some things. So where do earthquakes occur? Most earthquakes occur along the edge of oceanic and continental plates, along fault lines. We don't really care about what type of plate it is, oceanic or continental. We just want to know that it takes place on plate lines or fault lines, all right, at the edge of the plates. Here's some definitions. Obviously, the ones in reds are the ones we're looking for. So let's kind of go through the big ones, the big three here. So the first definition or key term we're looking at is seismic waves. And a seismic wave is just the energy moving outward from the focus of an earthquake. So now we need to figure out what the focus is. The focus of the earthquake is the location of initial slip on the fault where the earthquake begins. So the focus is underground, okay? The focus is underground, and obviously we know that's where it starts, and the seismic waves shoot out from the focus. The epicenter now is another key term, and it's the spot on the Earth's surface directly above the focus. All right, so the epicenter is normally where we see the most damage, obviously, because that's straight up from where the earthquake actually occurs. So these are some of the big terms. We'll have to see if you can pause the video now and jot them down before moving forward. Obviously, I'm just going to keep on going. Now, seismic waves and the wave types are the different. These are all also going to be on the quiz, guys, right? So we got P waves, we got S waves, and we got L waves, which are called surface waves. I call them surface waves on the quiz. So let's go into it. So P waves, okay, they're called P waves because they move parallel to the direction in which the wave is moving. Something that kind of makes it unique is that they move through solids and liquids. All right, keep that in mind because that's how we're going to kind of use we're going to use kind of what they can move through and how fast they move and kind of the damage they do. That's going to be like our categories we're looking at with the waves. So P waves, they move parallel, they can move through solids, and they can move through liquids. Now, S waves are called shear waves, but these move basically up and down. They're not moving parallel with the waves, they're moving perpendicular. Okay, so they're basically moving the opposite direction or against the grain. Oops. And then the last but not least, we have the surface waves, or L waves, or long waves. And for us, we just want to know that these do the most damage to structure in buildings because, again, they're taking place on the surface. And so for the quiz question is just, which wave type does the most damage to structures in buildings? Obviously, we know the answer now is going to be surface waves. So again, pause video here, jot down some more key terms. A lot of definitions today. When we're covering the basics. You got to know the language a little bit. So let's move along. Seismic waves properties. Another key term is velocity, and that's just the function of the physical properties of the rock the wave is traveling through. It's kind of, how fast. Think about velocity. Think about baseball. Velocity is just how fast you're throwing the ball. It's kind of the same thing here. How fast are the waves moving? And velocity can be affected by a few different things here. So you can see if velocity increases with rock density. So when the ground under the Earth's surface is pretty put together, and let's say it's like one solid foundation, then the velocity is going to be pretty quick. Compared to like, let's say, like sand or sand dunes, that ground isn't very dense. It's not really packed together because it's sand. And because of that, it's going to move a little bit slower and be a little less intense. Velocity changes when passing from one material to another, and that can increase or decrease depending on what's happening. Obviously, if we're moving from a less dense rock into a more dense rock, it's going to pick the pace up. The velocity is going to increase. Vice versa. If you're moving from a tightly packed dense rock into more loosely dense rock, then it's going to slow it down and make it less intense. Liquids, S waves do not get transmitted through liquids, and P waves slow down through liquids. So liquids are a big thing. It makes things less intense, less velocity, less fast. Now the question is, why is it important? Who cares? Well, for us, you guys can't really see there, but if we can measure the velocity, we can tell what type of rock is underneath the Earth's surface. So we kind of use this information to map the interior of the Earth. So it becomes really important for geographers. Let's move along. So now measuring earthquakes. This is another one of our central questions, is what tools are we using here to measure magnitude and other things? So here's the two tools that we're going to look at. And both these will be in the quiz. The first one is called a seismometer. And this is like the basic one. Okay, this is the instrument that just detects seismic waves. That's it. Okay, and as you can kind of see here on our picture, it's kind of what you would imagine. It's kind of the pen with the paper and it moves up and down. We've all seen it in movies. All right, but that just measures seismic waves. Now, the more advanced tool would be the seismograph. And the seismograph gives us seismic activity, but it also gives us a few different things. Records intensity, records height, and amplitude of the seismic wave. So we get a little bit more information from the seismograph. But these are going to be the two instruments that we're going to kind of be focusing on moving forward. Earthquake size, so how big or how intense or destructive was an earthquake? And we use two different kind of deals for this. The first one is the Richter scale, and I think that's the one that most people know is the Richter scale. And this one just measures the magnitude. So Richter scale measures the magnitude of an earthquake. All right, so let's write that down. Now with the Richter scale, it's important to note that when we're jumping up numbers, it's a massive difference, as you can see here on the bottom. All right, so if on the Richter scale, I think it's like 1 through 10, let's go through it real quick. So an increase from like if you were going to have an earthquake that was a 5 on a Richter scale compared to an earthquake that was a 7 on the Richter scale, if we just look at the numbers 5 and 7, they're not too far apart. Most people would think that those earthquakes are pretty similar in like damage and intensity and how big they were. But in actuality, for every number you jump up, there's a huge gap. Okay, so a 31.5 times increase in energy. So if we're going to jump to 5 to 7, well, that earthquake at the 7 is literally 992 times stronger than the earthquake that we had at the 5. So jumping up big numbers is going to give us big results, so there's going to be a big gap in between there. So keep an eye on that when we look at some of these examples here. And the Mercalli scale, this one just measures intensity. And the Mercalli scale is more like things that aren't really, they're not quantitative data, it's qualitative data, as we say. So it's more what you see, what you feel, things like that. So a lot of times the Mercalli scale is used to measure the destructive effect of it. I see the buildings destroyed. I see the streets tore up. All right, we call that qualitative data. When there's really no numbers, it's just more eyeball and visual. Okay. So let's keep it moving. You can see here on the Richter scale to give you an idea, an estimate of how many occur each year. But also for you guys that don't know the Richter scale, it's 1 to 10 for the most part. And as you kind of can see here, each number we jump up makes a major difference, as we said, right? So one of the largest earthquakes in the world, we're just going to kind of look at some examples now for the last like 5 minutes here. Another example would be, or one of the examples would be from Chile, which was one of the largest earthquakes ever recorded at a 9.5 magnitude, so absolutely massive. You can see the results here. And this one was a worldwide one. So it takes place in Chile. So we get, all the damage, all the destruction, all the deaths in Chile. But if we look at a map, right, Chile, then we get, 75 million damage in Hawaii. We get deaths in Japan, death in the Philippines, and 500 damage on the west coast of the United States. So this earthquake was so big that it was felt all over the world, different parts of the world. And we kind of talked about the places on the globe where, well, let's say they don't have like that financial backing to build structures the way they need to be built to make them safe from earthquakes. So in the lesser developed countries, we see a lot more damage and death compared to like the United States, right? Where we have the money and kind of the know-how to build the buildings to make them safe, especially in areas where earthquakes are prominent. Here's some other known earthquakes on record in the world. You can kind of just go through here, and you can kind of go through and see the damages and the deaths. Obviously, we know that the less developed countries are going to normally have the more deaths, like we said before. Earthquake damage. Here's some examples. You can get ground failure. Obviously construction collapses with the ground. We get fires underneath the ground. There's gas lines and electrical lines. Those break. We get a lot of fires through that. Landslides, tsunamis, which can become extremely deadly, and liquefaction, water saturated uncontrolled materials flow. So all these things could be a result of an earthquake. So earthquake is kind of the initial thing, and then there's some bad things that can happen afterwards to kind of make it even worse. All right. This is a landslide one. You guys can just read through this one on your own. Earthquake risk and prediction. You can basically, nowadays, we have like real-time maps or hazard maps and probability analysis to kind of help us keep track of where we think the next earthquake might take place. And obviously California here, as this is like the major place right on the fault line there. Short-term predictions. Here's some things that you can kind of see or do if you're ever in the situation. Foreshocks, normally you kind of get little tremors before you get the big earthquake. All right, and same thing, you also get aftershock after the earthquake. Ground deformation will be the other one that we're looking at. Basically, you can kind of tell beforehand the earth, the surface starts to move and deform, and the roads are already starting to break and whatnot before you can even get the major earthquake. Then I just want you guys to watch these two videos. This is Earthquakes 101. It's like 2 minutes long. Just gives us the basics. Same stuff we kind of talked about. And this one's kind of just an interesting one considering the World Series is going on right now. But in 1989, there was an earthquake during the middle of a game. Well, basically the beginning of the game in San Francisco. And I'll put this on the test question. It's kind of a fun one. It's an interesting video. So make sure you watch this one considering the World Series is going on right now. But that's basically it, guys. I know I only had 15 minutes to go through it, so I went through it really fast. I only have a minute left on my program here. So hopefully you guys pause, jot down a lot of the key terms. That's going to be a lot of the test questions. Obviously, everything in red is what we're looking for. And again, just go back to the first slide where it looks at the objectives. And then if you can answer those objectives, then you know you're squared away. You know you did a good job today, and you're ready to go for the quiz. But all right. That's all I got, guys. I will see everybody back tomorrow if you're at home, and we'll do a good job of reviewing all this stuff because I know I had to go fast. Hopefully you guys got what you needed, and we'll kind of fill in the pieces tomorrow. All right, see you later.